Hi all, welcome to week 9 of COMP9417, I guess it's semester 2, trimester 2 tutorial. So this week we'll be talking about the bias variance trade-off as well as some ensemble methods. So things like your random forest and your boosting. So first off, let's talk a bit about bias variance. I know I've touched on it in previous weeks, but let's just sort of talk about it a little bit more. So loosely speaking, we can decompose, the error. When you fit a model, when you see how well it performs, the error, which can be measured in a variety of ways, right? You can measure it. Some good ones, say mean square error is a very common one. Log loss, say. So this is just some generic concept of error, which can be measured in a variety of different ways. Say mean square error from your regression, and your log loss, say, for your classification. That there are a variety of different error metrics that we could be talking about, but just some sort of generic measure of error. And we can decompose it down into a few things. So we have the variance, the bias, and this little epsilon here, the residual sort of error. I don't know that we talk too much about this in the lecture slides, but the focus is more on the variance and the bias. So let's break down each component. When you fit a model and say instead of training data, and then you apply it to say the training data again, or the say the test data, right? There's going to be two sources of error that we typically care about: your bias and your variance, right? So bias occurs when the model is the model structure can't capture the real life construct. So likely, the model is too simple, or the model structure may not be quite right? So for example, let me give you a good example. You could have, say, some data like this. This is your target. Sorry, that's your feature, and this is your target. And you try to fit some sort of linear regression to it, right? So this one here, you're gonna have this model here is gonna have high say bias, right? Because the model might be too simple. In this case, it's too simple. The model structure might not be quite right. There's a bit of a mismatch between what we say the hypothesis space and of the hypothesis space here and what's happening in the data, right? So there's a mismatch here between the inherent structure of the data and the model that you're using. Now, of course, you and I visually could probably say that something like this, some sort of polynomial regression, would probably work better. There'll be very low bias there. Looks pretty good. The variance probably not too bad as well. But yeah, so in a nutshell, your bias is when there's a mismatch between your model structure and the real life construct, the construct in the data. So just think about this kind of example here. Now, on the flip side, variance is you can think of it as how stable the model is. How much will the estimate change given a different data set. So typically, what you'll find is that typically more complicated. Do a new line. Complicated models have lower bias and lower bias and higher variance. So the more complicated models, they'll have lower bias because it's more flexible. Typically, it's more able to capture the real life nuances. But then they have more variance because they tend to hug. They're too flexible. They tend to hug the data, the training data, too much. So, so when they hug, so typically hugs the training data so much, such that if you change the training data, then the predictions will change a lot. So this is one way to understand it, right? And this is a high bias estimator. let me give you a, maybe I'll just go, maybe this is, lower bias. Let me get rid of this. Let me give you a low bias estimator and possibly high variance. So something like, this, right? This estimator here would have, low bias. It's very flexible. You can capture the nuance of the data quite well. But if you swap out this data set for something else, it's gonna, it's gonna change quite a lot. So high variance, right? High bias. On the flip side, this simpler model here, this is straight line. It's relatively insensitive to changes in the data, so it's low variance, right? So this diagram here, it's quite common. You've probably seen it here and there. Tries to, if the target is like, say that the true or the actuals, right, and then the blue will be your predictions, right? So in something like, let's say this estimator here, this should be a high bias, low variance. So it would be something high bias, low variance. Yeah, something like this, right? The predictions don't really change too much. So that's this one. The predictions don't really like change too much if you change the data set, right? So think of each one of these dots as maybe a new data set, and then how close you are to the actual. But the problem is there's this inherent gap, right? There's this inherent gap between, real life and between real life and the model. So this little color, black, no, blue. So this little gap here, that's your bias. Ooh, that's a bad color. Yeah, fine. This gap there, that's bias, right? On the flip side, you have your green model here, which is your low bias and high variance, which is this guy here, right? And this general sort of spread, that's the variance, right? So you can think of each of these blue dots as a model to maybe a different subset of the training data, and it differs quite a bit depending on the training data, right? There's a few interesting things here. So, how could bias be observed in the estimation of error for a learned model? One thing to notice is that bias models tend to underfit. So again, think of this example here. A model of high bias, it tends to be less flexible, right? Less flexible to the point that there's a gap between the data, the way the data is, and then the structure of the model. So you can often see maybe a train score that's not too dissimilar to the test score, right? There's other ways to look at it as well. If the model is low dimensionality in terms of let's say I'm talking about number of features here, right? You can always plot the one ways of actual fit to see if the fit works well. So now when I say one way, what I really mean is you plot, say some feature, I call it xi, and then the target, right? And you might have something like this. Right, and then maybe you fit say this, right? And you fit say this, right? So this would be the estimate, and this would these are the actuals, right? These are the actuals, right? And like one way to go about, I mean, obviously if there's one feature, it's quite easy, but if there's many, you can kind of just have a view, have a look at each of these features one by one, or select a few features, maybe the top features, so you get a feel of whether there's some level of bias in the structure. So here I'd say there's showing a bit of bias. There's a gap between this curve and the straight line, right? The other thing about a biased model is that often the high bias models come to low variance. So if you change the data and it doesn't move too much, and it's probably going to be a higher bias sort of model, but also low variance. Two sides of the same coin. How can variance be observed in the estimation of error for a learned model? So there's a few different ways. One way I like is with the cross-validation, what you can look at is you can look at the standard deviation of the cross-validation scores, right? And this can be a bit of an indicator, right? So, you do, let's say maybe this is cross-validation, right? And then each one of these is a cross-validated model, right? If these, move a lot, that could be an indication that there's high variance in the data. If it looks more like this, then maybe it's a low variance, high variance in the model. If it looks more like this, it might be more like a low variance sort of estimator, right? Right. The really important one and most obvious one is if the test score is much worse than the train score, it's likely a low bias, high variance estimator. That's why they keep calling it a trade-off. Typically, often when you increase one, you decrease the other. So when you decrease your bias, you might increase your variance, and vice versa, right? Okay. There's another way to look at the relationship between model complexity and bias variance. So bear in mind that typically, all else equal, a more complex model, you're going to have lower bias and higher variance, right? Because you have more flexibility. In other words, more ability to capture the real life, the nuances of data, the real life data. But then, because you have that flexibility, you will tend to hug the data more. So when you change the data, the model will change a fair bit. So we visualize this by think about a decision tree, and this is, say, decision tree, but this is maybe the way the decision tree has cut the data, right? So it's maybe the first branch is pulse, second branch is temperature, third branch is age, right? You just keep splitting it that way, right? A simple model may only use pulse as a feature. So in other words, it'll be very simple. Be something just say you just have pulse, right? And then we have slow, medium, fast. And you have slow, medium, fast like that, and yeah, that's kind of it, right? That's your model, right? And of course, in each of these buckets, you'd have some data points. What's the target here? Oh, it's classification, isn't it? So it might have like, I'm just gonna make it up. So maybe your data set looks kind of like this, and you split the data like this, and there's one branch, slow, medium, fast, and here you'd predict red or negative. Here maybe 50-50, and then here in the fast you predict green or positive, right? This would be a simple model, and what I want you to understand is that it will have higher bias because look, we're trying to like capture all this complicated thing, right? Just using the one feature. I mean, the individual people observations here in each of these dots, it might be very different, right? So this kind of a model is going to have higher bias, right? This kind of a model will have a higher bias, right? But you know what? Like, it's going to have low variance. Why? Because there are many data points in each of these sort of buckets, so it's relatively more stable, right? On the flip side, imagine if you have a complicated model where you split it 3 times, you have three features. Each one of these buckets at the end, the leaf nodes, might only have like a few observations. So when you have only a few observations, right, it's going to be less stable, right? Each bucket, it's less of a sample size. There's going to be more variance as you switch out the data. But on the flip side, you are more able to capture the nuances of this complicated real life construct. So have a lower sort of bias. So there's another way to sort of think about it in the context of a decision tree, or it doesn't have to be a decision tree, but I feel like it makes the most sense of all these splits. Now, something I want to touch on, and we talk about this a bit in the Jupyter Notebook later, is some measures, right? Some measures of goodness of fit. So we have here our R-squared. R-squared is quite commonly seen in your linear regression. It's a measure of goodness of fit. It lies between 0 and 1, and its definition is SS stands for sum of squares. So you can think of it as the proportion, the variance explained by the regression model divided by the total variance. So it's a proportion of total variance that is explained, proportion of explained variance. So all your data moves this much, and your model explains this much of it, right? Proportion of total variance explained by your model, right? There's a few problems with R-squared, right? One is that when you add more parameters, the R-squared, it can't decrease really. So you run into the problem of it doesn't really penalize overfitting if you just keep adding more features or making the model more complex. It's just going to perform better and better. Now, in the context of regression, there's actually, I should say here, linear regression. There's actually many statistical tests you can use to perform overfit. So this is most commonly seen in linear regression, but you could apply it to any sort of regression, right? These ones, it's not the course, but if you're interested, these ones are commonly used in like statistical models and all that sort of stuff. Now, let's have a look at R-squared in the context of bias and variance, overfitting and underfitting. Now, on the left, we have a simpler model. This may be something like this. Right? On the right, you have a more complex model, which might be something like this. Maybe there's 10 of them, right? Beta, like 10. Right? Actually, no, sorry, it's a polynomial, isn't it? So, I don't want to write all the polynomial terms, do I? So there's plus beta 2x2, x1 squared plus, and all the cross terms. Just think of all the polynomial terms of, say, order 10 or whatever, right? But anyways, this is going to be more complicated, right? Now, no. So, it's probably obvious enough just visually that this is underfitting. It's a straight line. It's not really quite complicated enough to capture all the nuances of the model. This one, most people would say is, it's overfitting. It's hugging everything a bit too closely. It's not quite right. I think we can all agree with that. But what do we notice about the R-squared or the training validation? It's quite similar, isn't it? So, this is very, very similar. The variance in terms of I guess here the training validation is low, but the difference between these two, it's kind of similar, isn't it? Right? It's kind of similar. Have a look at the other side. When it's over really hard, this is really, really good, right? This 98%, that's fantastic, right? But this is just terrible, It's absolutely terrible. You've overfit so hard to the training data. When you get the validation data, it's just rubbish, right? And maybe the validation data, maybe it looks like, maybe the validation data looks something like this. And then, so where you get really thrown off is like here. This is going to give you a huge error. Here is a huge error, etc., right? Which way does that go down? Okay. The next thing we'll see in a bit when we look at the the Jupyter notebook, is the validation curve. Now, validation curve. So yeah, typically we keep talking about this bias variance trade-off, right? So what is this trade-off? So typically when you increase the model complexity, your bias goes up, but then this sort of decreases, but increases the variance. And so it will come to the point where you increase model complexity, the bias keeps going up and up, the bias keeps going down and down and down, but at the same time the variance keeps going up and up and up. So you just find this point where it's sort of optimal, right? One's going up, one's going down, right? If I find a graph, maybe I'll draw it. So it might look something like this. So say this is bias, right? Your bias is kind of just going down, 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 down. Let's call this bias. And let's say this is your variance, and your variance is just going up and up and up and up and up. That's your variance. right? You want to find the optimal point, right? It's not necessarily the crossover point, but it's just like, whenever you add the two up and it's the lowest, and maybe here, maybe there, that's the optimal model. And maybe if I draw like the total error, or maybe look something like this, right? This is total error, right? And then I guess residual error might be something like, I won't draw it, but yeah. So the best model will be here, right? This is the best model. Yeah, so this is typically what you find, and this is some sort of measure of model complexity. Just like that. Cool. So something called a learning curve, right? And it's here we go. Yeah. Learning curve has on the x-axis your model complexity, and it's used in order to find the optimal level. Now, this is sort of like a theoretical sort of graph, right? You typically don't break this down. You probably use like the training and validation score, and what you'll see is, with the training score, typically the more you can just keep making the model more and more complex until you overfit really, really hard to the training data. So typically this doesn't really go down, it just keeps going up. Now what you care about is your validation score, right? There's going to be like a point where you've crossed over, and then you've started possibly overfitting, right? So over here, you could say maybe you've overfit, and over here maybe a bit of underfit, right? Right. Oh, actually, this graph is there. So this graph here kind of demonstrates this a little bit. So let's have a look at the colors. Mean square error and flexibility. So which one is which? That's right. One is training, one's validation. Yeah. So the red should be your validation, and your gray should be your training. But you have these points here, right? So the gold is like, well, this gold line here, and then the blue is that blue line there, and the green is this little funky guy here, right? And you can sort of see, what's kind of happening. And this is, this flexibility there is really, we're talking about polynomial order, right? Because this is a linear model. So you can also think of this as order, or what polynomial order they're using here, right? So the linear one, it's underfitting, it's probably no good. Let's increase the flexibility a bit, and what the blue is this sort of maybe quartic something, so maybe order 4, some simple enough polynomial, and it's sitting there. And then we try to make it too complicated, the green, and we're back up, right? But notice here how, like on the gray, the training data set, it always goes down as you add model complexity, but it's only on the validation you see. Yeah, cool. So I want to talk about the first ensemble method that we'll sort of come across. It's called bagging. Now, bagging here is short for bootstrapping and aggregating, right? The way this works is, think of it as averaging stuff out to smooth the results out, right? So you might notice this sort of statistical phenomenon, right? Like when you take samples, it's usually better if you take a bunch and then average it out. So like if you're trying to work out, I don't know, say the average weight. There we go. I got it this way. If you're trying to work out let's say the mean number of children in a family in Australia, all right. The population is, if you knew everything, all 25 million people, you asked everyone, right? That'll be the real, right? But let's say you're doing some sort of sample, and this is what we're really doing when we're doing these models, right? We're taking a sample of data, say the training, and trying to extrapolate it out to training and valid and other sorts of data, right? Now, hope you appreciate that. If you take many measurements, if you ask many families, and average out the number of children, it's going to give you a better estimate. Why? There's sort of less variance, right? I mean, this shouldn't really have any bias when you ask this question, but the concept here is bootstrapping and aggregating is where you're basically you're decreasing the variance through averaging, right? Decreasing the variance through your averaging, right? Now, the nuance here is that you're using the same data set, right? So bootstrapping is kind of funny. So bootstrapping is really, so there's two things. So there's bagging, maybe I should start bootstrapping. Bootstrapping is a statistical method where you estimate some sort of property or property of an estimator by sampling with replacement. So let's say you have a data set, say 1,000 observations. You might sample 1,000 from there, right? With replacement, right? So you could get several of the same observation. So think of it as a way of you're sort of artificially, it's pseudo data, right? So you're artificially just generating more data, and then each of those bootstrapped sets of data, you fit some sort of model to it, right? Some sort of say decision tree or linear regression or what have you, some sort of machine learning or statistical kind of model, right? So that's effectively what bagging is: bootstrapping and aggregating. So bootstrapping in the sense that you are taking, say, your training data, and you are sampling with replacement, and you just maybe say 10 times to create 10 data sets, right? 10 pseudo-ish sort of data sets, right? You fit a model to each one, and instead of just taking one estimator, you take the average of all the estimators, right? Thereby decreasing the variance of the prediction and possibly increasing the overall training accuracy or error, right? In general, bagging can decrease the variance of any algorithm. It can just be generically applied, but of course, it can't cost compute, right? So on the following page, I've just got a bit of background sort of maths. You don't need to know it. It's just, some talks about variance and this and that. Just some ideas as to why bootstrapping can decrease the variance, but we don't really need to cover it. Cool. So that's bootstrapping. Bootstrapping is typically applied to, we can apply to anything really, but in this context, we're looking at it in terms of decision trees, right? And it's great because decision trees are a low bias, high variance estimator. So when you bag it, you curb a lot of the variance, which is fantastic, right? Now, moving on to random forest. So random forest is a development on top of your bagged decision trees. So in general, this is a concept in the statistics. When you take the average, from the previous slide, when you take the average of a bunch of things, right? You can decrease the variance if each of those things are decorrelated, right? If they're correlated, you lose that variance reduction effect. So the way when you think about it is, your random forest, they're bagged decision trees, but you find a sneaky way to decorrelate all the trees. And the reason you do that is when you then bag it, it improves performance because when you have things which are correlated, you don't really get that as much of a variance reduction effect when you average it out. So the way we decorrelate it is, you do your bag trees as per normal, but then each tree is only given a random subset of features. Often the square root of the number of features is quite common, and it's a hyperparameter you can tune. So you do your bag decision trees, but just each decision tree you only get a random subset of features. So that's the key difference. So for example here, let's give you a toy example. Bag decision tree. You have a data set of 10,000 observations. You can create 4 bootstrap data sets. So you get each of 10,000 rows. So you sample from the original data set 10,000 times with replacement. You fit a decision tree to each of these bootstrap data sets, average out the predictions of all the bag trees, and that's your final prediction. Now the next one is your random forest. Let's go through this again. So it's quite similar. We have our 10,000 observations. We create 4 bootstrap data sets. If you fit the decision tree as per normal, the difference here is that each decision tree will get a random subset of features to build the tree from. Because you can imagine, right, with those 4 bootstrapped decision trees, they're probably going to be like reasonably similar, because, well, you're building the tree on the same sort of data set, right? So when you give them each a random subset of features, they're less likely to be similar, hence decorrelating the decision tree. Hence the variance reduction effect from bagging is improved, and often it will improve the performance compared to your bagging. Okay. Next we have our boosting. So boosting is another. I should probably say. So all these methods are called like ensemble methods, and it's because it's an ensemble. You ensemble or combine a whole bunch of, machine learning algorithms. A rather powerful one is your boosting. It's very popular in industry and in Kaggle. It's a very powerful way of doing things. So the way it works is you ensemble together many weak learners, say a stump. So a stump is a decision tree with just a few branches, hence a stump, not a full tree. You've only got the bottom bit. So with your random forest and your bagging, often it's more of a variance reduction kind of effect. Boosting and reduces bias, but also variance. It can work on the both of them, right? So there's a couple of interesting ones. ADA boost or adaptive boosting is one of the earlier ones. So the difference here is that also it's done sequentially. So let's look at this diagram. You're building a single decision tree. Okay, it's just one. With bagging, what you do is you take a random sort of subset. You take a random subset each time, and then you build a decision tree, and then you can average it, right? But you can do this in parallel. With a lot of your boosting methods, I mean, I know that like some of the more powerful ones like XG boost, you can actually do a bit of parallel processing, but your stock standard boosting, typically it's sequential. You have a data, you fit your model, and then you look at say the errors, or you readjust the weights. You keep feeding, and then you sequentially might have like say 250 trees, and you sort of combine them all together to form your prediction. That is your gradient boosting machine. So at least for the case ADA boost, the errors of the previous model provide the training weights for the next iteration. So you get your model to focus on the areas that you were not so good at. Right. Next thing I want to talk about is GBMs. GBMs are quite popular. Stands for gradient boosting machine. So I think the algorithm is quite interesting to look at. So what you do is you split your data into capital B like bootstrap data sets, right? You bootstrap it say B times. You fit a decision tree, this F hat B with D splits to the training data, right? This is your prediction function, right? Every iteration you add to your prediction function, you add a tree to your prediction function. So you gradually a GBM is made up of many trees that are gradually sequentially grown, right? So you split your data up, and then you grow your first tree, right? But you only give it like lambda. Lambda is some learning rate, say 0.01, right? Like you fit your tree to the first bootstrap data set, and then you add lambda, the learning rate, times that to your prediction function, and then you update the residuals. So you get rid of the predictions from the first model. So you gradually whack away the error. So if you start with a base model of nothing, then and you're trying to compare it to the real data set, you gradually just sort of knock off bits, like portions of trees that you sort of add up, right? In the end, you have your final boosted model, which is just like the aggregation of everything, and of course you have to remember the learning rate. Cool. Let's move along to the Jupyter notebook. Right. Cool. So let's talk about bias and variance. Some questions here. How could bias be observed in the estimation of error for a learned model? I think we spoke about it briefly up here. There's a few different ways. Where did I write it? Yeah. So often if the train score is similar to the test score, it can imply some sort of level of underfitting, which goes hand in hand with bias often. You can also do some plots depending on how big the data set is. Depending on how big the data set is. If the data set is like small enough, you can do a whole bunch of plots, and just sort of have it like something like this, right? And have a look if the model structure is good enough or flexible enough to fit the complicated data, right? Cool. Second question is, how can variance be observed in the estimation of error for the learned model? So a few different ways. You have your CV score, so your cross-validation score, right? You might do like say 10-fold, and you can look at the standard deviation of all the performance metrics of each of the 10 folds, and if the model is low variance, it will tend to be more clustered together. If it's a higher variance, it will tend to have a high variance in the scores for the the performance metric for training versus test. Yeah. So what do we do is generate some models, make some models. We talked about the example earlier before in the slides. So this is clearly underfitting because it's too simple. It's not flexible enough to capture the nuances of the data. This one has hugged the data way too closely. It's going to be no good in terms of generalization. Right. Yeah, so it's a similar sort of thing here. The thing to note here, that what they're trying to draw attention to is the R-squared. So as touched on before, typically when you underfit, the performance metrics might not be so dissimilar, and when you overfit, it looks really good on the training data, but then on the validation data, it sort of falls off a cliff, and it's just nowhere near as good. We talked about the validation curve already, in our lecture slides. Where there's that trade-off, right? So here the reduction in bias is worth the increase in variance, and then sort of then after here the reduction in bias does not justify the increase in variance. This is a learning curve, kind of seen here. So you kind of just want everyone sort of maximize, but you probably pay more attention to the validation curve than the training curve. All right. So what have we noticed actually? High bias learners tend to underfit, and high variance learners tend to overfit. Why is that? So high bias learners tends to be too simple. So maybe just a straight line. Now a straight line is very insensitive to outliers. It's relatively insensitive to weird data sets. High variance learner will tend to hug the data more, so they'll give you more flexibility, but will tend to overfit because it's more hugging the data more. Right. Now let's have a look at a decision tree example. Cool. So you have 1, 2, 3, 4. You have 4 different classes, and you want to build a decision tree to separate all these sort of four classes, right? The one thing they're trying to sort of flesh out here is that with enough depth you can it gets better and better, but with enough depth you can perfectly classify everything, which will tend to overfit. So the decision trees are a high variance, low bias estimate. It's incredibly flexible. There's a lot you can do about it. Oops, sorry. As I said earlier, the flexibility in the decision tree has the potential to completely overfit to the training data. Yeah. What I want to see is this here. So we can see it's basically I think it's almost these two are like perfectly classified, but you can see this shape is a bit odd, right? This is not what I would draw, as a human looking at this. So even though this is perfectly fit to the training data, on the validation data set it probably won't be as good. Maybe something like this is better. Question: what can we do to make use of multiple overfitting estimators to reduce the effective overfitting? So we learned a few methods of ensembling that were great in terms of reducing the variance. So bagging, random forest, and we could also use a GBM if we want to be extra fancy. Yep. So there we go. Got that. Yeah. So this is the bagging tree. Sorry. This is a decision tree. And notice how sort of stepwise and sort of angular it is, right? But it's only when you sort of bag it, you get this sort of smoother effect. And I think this is a better fit, right? This gives more comfort. These lines seem to make more sense than the sort of simple decision tree. The next thing I'll talk about is your random forest regression. So your random forest regression, so keep in mind, it's like your bagged decision tree, except you are randomly assigning each decision tree a set of covariates or independent variables or features in order to decorrelate the model a bit more. Now, of course, you can use the random forest as a regressor, but also as a classifier. They both work, right? So in this case, use as a classifier, but of course, it can also use as a regressor. As you can see here, we've got this sort of like wavy pattern here, and we fit the random forest to it. It's doing quite okay. We can also use your random forest in the context of classifying digits. So this is the the MNIST character recognition, the famous MNIST character recognition data set. So we plot it all. We can see, look, these are numbers. 5, 0. We've got to create something that can predict this, right? We'll decide to use the random forest classifier here. Of course, we have to first split our data to train and test, etc., etc. Then instantiate our model, and then we just fit and predict. Now, looking at this, it's actually alright. Like, the precision recall is actually looking pretty good. It's like in the high 90s, right? So your 98% here, it's looking very, very good actually. And we can see here, this is a confusion matrix. So this is the actuals and the expected. This was only 1, 2, 3, 4, 5, 6, 7. There's only 7 misclassified numbers, which is pretty good. Given how many digits there are there, right? So even without any hyperparameter tuning, we can actually see that this random forest is actually performing quite well, and with a bit of hyperparameter tuning, it might perform even better. Okay, so what advantages does the random forest have? It is very fast because we can decision trees themselves are quite simple, but we can also parallelize it. It's not reliant on the previous decision tree. Right. The multiple trees allow for probabilistic classification. A majority vote amongst gives an estimated probability. So if you're doing a classification problem, you have like 100 estimators. That can be used to generate a probability, so you can get a probability for your classification. Now, it's non-parametric. So recall non-parametric means the number of parameters are set before you begin modeling. But also on the flip side, parametric means that the number of parameters can grow if you increase the number of say parameters. Yeah, it's very flexible. Yeah. Now, what disadvantages does the random forest method have? The main disadvantage is the lack of interpretability, but this kind of applies to a lot of methods in machine learning, like neural networks, GBMs, etc., etc. But there's ways around it. You can use feature importance charts. You can use what is it called? You can use the partial dependency plots. So feature importance charts show you the features that are the most important. Partial dependencies show you the shape of the relativities, or I guess like the effect each factor has on the target. So they're very, very useful. The next thing I'll talk about is boosting. So boosting is very, very powerful. It's one of the more complex versions of ensemble learning. So you fit your model, right? And like your dad or you fit your model. With the boosting, right? The way it works is that the base learners are not independent. It's a sequential sort of learning model, right? You use typically weak learners, so things like decision trees, and you incrementally build and build and build and build and build and build and build. And it's incremental in the sense that it builds off the errors of the previous base learner, right? So you fit a base learner a stump, right? And then you fit another one and you fit another one, but each time you adjust and shift based on what's happened before. So each boosting iteration is used to reweight examples before the current iteration begins. So this is ADA boost, this is adaptive boosting. There's other different ways, but in general, back to this diagram here, it's sequential, and the stuff that happens before has a big impact, right? Right. What's next? Okay. So what can we see after we run each boosting algorithm? We can see that the time each is pretty good. The thing we see is that, at least in the next example, we're fitting a bunch of weak learners, right? So you can see it's a stump. So in a sense, each of these learners can really, this is a stump. It's only like 2 branches, right? Like this side or that side. So you can see that it splits it up using that straight horizontal or vertical line, depending which feature it's splitting on. So yeah, so this, I won't get into the details of this one, but this is a boosting machine, an ADA boost model built from scratch, and we can see it in action here. So depending on how many iterations, each one of these is a weak learner, right? So you fit the first one, and then you reweight, and then you look at the errors of the previous one, and you fit again, and then you reweight, and you fit it again, and just keep like iteratively building on, and finally in the end, oh yeah, here we go. So the key point is that, look, so this is the original training data, right? Using just like a straight up, we could just use a straight up decision tree, but using a stump, we can't fit it, right? A stump can only really, with one split, can really only do like a straight line horizontally or vertically. The first split goes straight down on 0.4, so it splits along here, right? So after splitting on that, you can see the errors, right? It's based off these two, right? So you split again, and then iteratively just sort of whack away. I guess you readjust the weights, so you focus more on the ones which are mispredicted or predicted incorrectly. And here is the learning curve here. You can see, over time, you can see the training error always has to go down, right? So this is all the way down until it's perfect, right? Here it's hard to overfit because it's I mean, it's such a simple sort of data set, right? That even when you sort of get all the way to the end, right? Your training and test, sort of, flat lines here, right? Cool. Right, what are some things to note? Yeah, so note here that, like, it created the the best model after less than 5 iterations. These ones here were kind of wasted, so in practice you might just want to cut it off here. There's no point having all the extra iterations there. And there's in your boosting packages, there'll be things like there'll be parameters such as early stopping, which basically stops the boosting algorithm when there's no further reduction error for some sort of amount of time. Anyways, look, that's all for today. I thank you for your time, and I look forward to chatting with you in my console times. Thank you very much, everyone.